This is the 3-carat round plastic mounting set in platinum.
Yeah, that's really pretty.
I hereby pronounce you engaged.
That's the one. Looking at rings has been great.
All right, so
Which one of these? I hereby pronounce you engaged.
Really pretty.
diamonds will sparkle only at a given angle. All right, so you will see the escaping light at that
Yeah,
angle.
that's really
And light escaping at that angle
pretty.
will be experienced as sparkle.
I hereby pronounce you engaged.
That's the one. Looking at
So why are diamonds so good at
Looking at-
sparkling?
looking at
That's a sparkle, right?
looking at rings has been great.
All right, so what's the sparkle? And why are diamonds so sparkling? All right, so a couple of things that we need to know regarding the reason why the diamonds sparkle is the following. Number one, the light coming from a denser medium into less dense medium is going to refract away from the normal. It's going to bend away from the normal. This is water, this is air. And so the light coming from this light source is going to end up bending away from it. All right, so let me check to see if we got the stuff that I need. All right, I don't see the details. All right, so let's talk about the critical angle. This is known as a critical angle right at this point. Critical angle is known as a critical angle because it's critical to whether the light escapes from the medium. In this case, it's light's escaping, or it's going to be captured by the medium. So this is the captured light. So right at the critical angle, and this is the angle of incidence, the critical angle. Notice that the refracted light is going to go parallel to the boundary. So at the critical angle, the refracted light goes parallel to the boundary. At the critical angle, the refracted light is going to be 90 degrees to the normal. So at the angle of refraction is going to be 90 degrees when the angle of incidence is the critical angle. So what happens if the angle of incidence is smaller than the critical angle? Notice that this is the critical angle, and this is smaller than the critical angle. When the angle of incidence is smaller than the critical angle, light is refracted, which means that the light is able to escape from the medium. At an angle smaller than the critical angle, light escapes from the medium. That's what it means. So what happens to light at angles larger than the critical angle? This angle is larger than this one. At angles larger than the critical angle, the light is going to get totally internally reflected. So at angles larger than the critical angle, light is experience internal reflection, total internal reflection. At angles larger than the critical angle, there's no refraction, no light escapes. So summary statement is, at angles smaller than the critical angle, the light escapes. At angles larger than the critical angle, the light is captured by the material. All right, so this is placed here as a summary statement. So you got your critical angle here. If the incoming light is smaller than, if the incoming light is coming at an angle smaller than the critical angle, the light is going to escape. At angles larger than the critical angle, it gets totally internally reflected. So it's going to be captured by the material. The reason why the diamonds sparkle is because diamonds are really, really good at capturing light. So the question is, why are they so good at capturing light? All right, we got the best answer. Whenever you're ready, just jump in.
C.
Which one did you say?
C.
All right, I'm going to give you 2 points for saying C. All right, so if total internal reflection occurs at the boundary, all right, so what does it mean? If the total internal reflection occurs at the boundary, notice that no light is escaping from that medium, right? So no light is being refracted, if that's the case. So the best answer is A. Those of you guys who pick A, give yourself 2 points. So if there's total internal reflection, no light is going to be able to escape from the material, which means that there's no refraction. So no light is being refracted. Does that make sense? All right, so the best answer is A in this case. It's kind of neat. I like this picture. So they have some kind of a light source here. And notice that this is smaller than the critical angle, so it escapes. Smaller than the critical angle, so it's going to escape. And this one is larger than the critical angle. This actually gets internally reflected. All right, so diamonds sparkle because they're good at capturing light. All right, so the question is, why are they so good at capturing light? Part of the reason is, that's part of the reason, not the entire reason. Index of refraction of diamond is extremely large. It's 2.5, which means that the light slows down. And the larger index of refraction is going to give you a smaller critical angle. The larger the index of refraction is, smaller the critical angle becomes. Why? Something we'll investigate later. All right, so the only thing you have to know is slower the light moves, the smaller the critical angle is. All right, so slower the light moves through the material, the smaller the critical angle becomes. And then the diamond is cut in such a way that much of the light, when it's captured, is going to internally become reflected. So which means that the light is going to be captured by the material. As the light is bouncing around, only at certain angles, it's going to be able to hit the boundary at an angle smaller than the critical angle. So if the light comes in at an angle smaller than the critical angle, it's going to be able to escape from the medium. All right, so short answer is diamond has an extremely large index of refraction, meaning that the light slows down quite a bit in diamond. And the critical angle is directly proportional to, inversely proportional to the critical angle is going to be related to how much the light slows down. So slower the light is moving, the smaller the critical angle is. So we'll come up with the mathematics for it later. So only at extremely small angles, the diamond is cut in such a way that it's going to be able to escape from diamond. So the escaping light is going to appear as a sparkle. All right, so the fiber optics in essence works the same way. This material has an extremely large index of refraction. And so it has a very small critical angle. So the light does not get a chance to hit the boundary at an angle smaller than the critical angle. So it doesn't really escape from the medium. Dispersion is breaking white light into its color components. This is known as dispersion. So breaking light into its color components. And notice that you got red on top, violet at the bottom. I usually do a comparison between red and blue. And the spectrum obviously is between red and violet. All right, so which one? Why is it that red is on top, the violet is at the bottom? If you had to guess, what would you say?
Wavelength?
All right, so let's ignore the wavelength for now. Why is it that red on top, the violet is at the bottom?
The red's not traveling as far through the prism.
Okay, yeah,
Or
that's
is it-
fairly obvious, right? All right, the bending is caused by the speed, obviously. And then you notice that the red is bending less than violet. All right. So it's bending less than violet, which means that red is traveling faster than violet. So the question is why? All right, so, and here's the reason why we end up spending so much time on the wave theory, right? Okay, obviously, you can kind of guess that the wavelength is going to matter.
So red would be like, because it has a longer wavelength, it has fewer, the frequency is lower. So would that be like
Okay,
less
cool.
energy
Absolutely.
going into, so less of those atoms hitting each other, and that affects the angle somehow?
Hmm. Okay, I like the way you're thinking. I'm going to give you 10 points. It's right or wrong. It doesn't matter right now. And then we'll have a short little discussion. All right, so the wave speed can be expressed in terms of frequency as well as the wavelength. What do we know? If the frequency at the boundary is constant. All right, so with that assumption in mind, you know that the larger wavelengths will travel faster, right? That's it. All right, so which one has a larger wavelength? You know that the red is going to have a larger wavelength than violet. As a result, the red is going to travel faster, provided that the frequency at the boundary is constant. So, damn. All right, so question is, why would the frequency at the boundary be constant? So if the frequency at the boundary is constant, the larger wavelengths will travel faster. All right, so larger wavelengths will travel faster, so red is traveling faster than violet because it's got a larger wavelength, which implies that the frequency at the boundary must be constant. So all right, before we discuss the reason why, let's just focus on this one. So you got the incident light going through a prism. Different wavelengths will travel at different speeds. Larger wavelengths will travel faster, which means that different wavelengths will have different indices of refraction. Indices of refraction tell you at what different speed, what speeds, how much the different colors slow down. All right, that was mouthful. All right, index of refraction. Let's just go over some of the numbers. So I'm looking at, for red, it's 1.52, and then for violet, it's going to be 1.53. All right, so which means that the violet is moving much more slowly through the material than red does. And what that means is red is moving faster than violet. So different wavelengths will experience different indices of refraction, which means that they will move at different speeds. Okay, pick out the best answer.
All of the above?
Okay, so that's all of the above. All right, Well, let's investigate. That's not
I retract my answer.
okay. So I'm more interested in the reason why you retracted your answer. So what is it that you saw that you didn't like?
Because it says that for B and C, longer wavelengths are refracted more. And red is refracted the most. Those are backwards.
Okay, yeah, definitely the red is refracted the least, so C's no good.
So A is the answer.
Each wavelength of light is very good. I'm gonna give you 10 points for saying the wrong thing and then backing out of it. Okay, so A is the best answer. So those of you guys who like A, give yourselves 2 points for that one.
D.
B.
Okay, all of them kind of look right. Some of these questions, which are really, really tricky, used to be essay questions, and I just collected some of the answers, and most of them look right, but something is missing. And I think the best answer is dispersion occurs. It happens within the same material, obviously, so which means that material is going to slow down some wavelengths more than the others, right? So B is the best answer. So those of you guys who said B, 5 points. Those of you guys who picked B, 2 points each. All right, so that was actually pretty good. All right, one of those questions about your childhood. Everybody ponders about this question in particular until they give up. Why is the sky blue?
It reflects the ocean.
I like that answer. Yeah, so that's one way of looking at it. I'm going to give you 5 points. That's the most common and most intuitive response that you can come up with. All right, so you will say the sky is blue because the light is reflected from oceans. All right, what else can you come up with?
Why is the ocean blue?
Why is the ocean blue? Because the light
It
is
reflects
reflected
the
from this. Yeah, I'll give you 5 points. Both of you guys give yourselves 5 points. All right, I need more. What else?
Refraction.
Say it again. All right, so refraction, explain that a little bit more. Because the refraction is
It's in the sky. It separates the colors so that we receive in our
okay,
eyes.
go ahead. Refraction. Okay, kind of like refraction. Cute. I should probably move this here. Okay, this is a little bit more deceptive, so I'm gonna move that. It's actually cute. Okay, I hear this one, the refraction, quite a bit. Okay. So the light is coming from space, and then boom, hits the atmosphere, and the atmosphere is kind of curved, right? So the colors get separated, and which one bends the most? It's going to be blue, right? So it's going to end up bending to your eye. So refraction is the reason why the sky is blue, right? All right, so this was, Tim, I'm going to give you 5 points for that one. Who wants to say this argument is not valid?
Okay, why isn't the sky violet?
Okay, very good. I'm going to give you 10 points for that one because it looks like the blue is at the bottom. In reality, violet is at the bottom. So if that explanation were correct, the sky would be, it would be violet, not blue. So we have to look for an explanation which is other than what we came up with. Despite the fact that the explanations that you guys came up with are kind of valid in a sense. All right, I still remember when I was an undergraduate student, all right, being a recovering pervert that I was really interested in this girl, and she had a boyfriend at the time, so she put me on the bench for a while. And then after the breakup, all right, so we started dating, and that was like one of the first questions that she asked. She said, "Oh, so you're a physics student, right?" I said, "Yeah." And then she goes, "So if that's the case, I've been wondering ever since I was little." She said, "Why is this sky blue?" And I'm looking at her, I'm thinking, "Oh, I see what the problem is. The problem is mistakenly people think that we actually do physics in physics classes. In reality, no, guys. The stuff that I'm emphasizing is not the stuff which gets emphasized in physics at all. I have a very strong conceptual approach because I'm trying to follow in the footsteps of my hero, Richard Feynman. All right, so I want you to have a really good understanding of what's going on before we get the mathematics on top of it.